Okay, so the second law says that the change in the entropy of the closed system must be greater or equal to zero. So it just means that it cannot decrease. Okay, so let's talk about this in a little bit more details. So let's just assume that we have two heat baths, right? For example, outside the room and inside the room. Okay, so I'm gonna draw that in this way. So the hot side, let's say, is TH. Right, so let's say TH is equal to, let's say, 400 Kelvin. Okay, that's a little bit hotter than what we are experiencing nowadays, right? But just for the sake of argument, let's make calculation a lot easier. And then let's say we have the cold side. Some trouble drawing. So TC, and let's say TC is simply 300 Kelvin. Okay, so let's allow some exchange of heat between the hot side and cold side. So we're gonna call the whole thing as the closed system. Okay, so our system contains both the hot bath and the cold bath. So if you have heat going between these two, it's fine because it's within the system. Okay, so in the closed system, anything can happen, but you don't allow any heat to go in from the outside, right? So that's not closed, right? So for closed system, this is fine. So we know from our experience that heat gonna flow from hot to cold, right? So let's say we have heat Q flowing from hot side to cold side, and let's say that's gonna be 100 joules. So let's calculate the change of entropy of this closed system, right? So we're gonna divide our calculation into two parts, the hot part and then the cold part. So the change in the entropy of the hot part, so from the point of view of the hot part, it losing heat. So delta Q is negative, which is the same as what we had earlier. Okay, so delta Q divided by temperature. What temperature do we use here? Well, if we're talking about temperature of the hot part, then it's the temperature of the hot side. So that's going to be minus 100 divided by temperature of the hot side, which is 400 Kelvin. So it's going to be minus 1/4 joules per Kelvin. So that's going to be the change of the entropy of this part of the system. Now the system also contains the cold part, right? So we cannot ignore that. So let's talk about delta SC, which is the change of the entropy of the hot of the cold side. Now the cold side receive heat, so delta Q is positive, right? But delta Q is still 100 joules because everything that you get from hot must be going to the cold side, right? You cannot lose any energy, right? But the sign is going to be different, so it's going to be 100 divided by, sorry, let me just write it out first. So delta Q divided by T cold, so that's going to be 100 over 300. So that's going to be 1/3 joules per Kelvin, like this. So the total change of the system, delta S system, is going to be the change of the hot side plus the change of the cold side. Right. So if you calculate the number, the hot side is roughly going to be minus 0.25, but the cold side is going to be plus 0.33. Right. So in the end, you're going to have delta S of the system to be plus about 0.08 joules per Kelvin. which is positive. So this is fine, because remember, the change of the entropy of the closed system must be greater or equal to 0. In this case, we have it greater than 0, 0.08. This is fine. Now, let's assume that what if the heat flow from cold to hot? So let's just reverse the direction of this diagram. So just to make it easy, I will just copy and paste here. And then I will just reverse the direction of the heat flow. Okay? So now instead of flowing from hot to cold, it's flowing from cold to hot. And let's just put a small division here so that it's clear what we are talking about. So all the calculation is almost the same except you flip the sign. So I'm gonna go a little bit faster here. So delta SH is gonna be plus 100 divided by 400. So that's gonna be plus 1/4 joules per Kelvin. And T cold is the same except again the sign is reversed. So it's gonna be minus 100 divided by 300. Okay. So make sure you understand why the sign of is reversed, right? It's because we reverse the direction of the flow of heat. So that's going to be minus 1/3 joules per Kelvin. So now if you add the change of the entropy of the system, which is same as before, delta SH plus delta SC, you're going to have negative 0.08 joules per Kelvin. So in terms of conservation of energy, there's nothing wrong with this, because all the energy that you extract from the cold side, you put it in the hot side. So there's no energy lost, there's no energy, spontaneously created. So you don't violate first law of thermodynamics. You don't violate the conservation of energy. But you do violate the second law, because the change of the entropy now becomes negative. And this is a closed system. It cannot do that. So that's why you will never see, okay, unless you do something more than this, you will never see hot bath and then cold bath just placed together and then heat gonna flow from cold side to the hot side. You cannot have that, right? But, you might ask, okay, but the air conditioner is doing that. The air conditioner is taking heat from inside the room, which is colder than outside, and then dump it out to the outside, right? So isn't that in violation of second law? Well, not really, because in that situation, you are not just doing this, okay? Because heat flow, like the way we are drawing like this, is just happening without us doing anything, right? But what we can do is we can force the flow of heat from cold to hot, but you need to put in some extra energy to do that. So it's no longer going to be a closed system. You have to have some influence from outside the system in order to get this. Okay, so and that's going to be kind of the where? Say that again, please. I don't understand what you're asking. Well, in this calculation, I'm talking about two cases. So the top one, we assume that heat flow from hot to cold, which is what we expect. And I'm showing that if this is the situation that we are talking about, then the entropy change of the system is positive, which is fine. But what if we allow heat to flow from cold to hot like this? You're going to see that the change of the entropy is negative, which in violation of the second law. And that's why it doesn't happen in real life. So yeah, okay. So I should be clear that this is in violation of second law. So this will never happen. Okay. Okay? Okay. So again, this is to show that if you allow this to happen, then you violate second law. And second law is probably the only law of physics that you can never violate. Okay? So this will never happen. So heat always flow from hot to cold. Right. But again, this is for closed system, right? So if you allow the system to not be closed, then actually there's a way to move heat from cold to hot. And that's kind of the reverse of the heat engine, right? So if we have the heat engine again, and what we have is the hot side, TH, and then we have the cold side, TC. And again, the heat engine is extracting heat from the hot side. A little engine here, you extract some work out to do whatever you want, and then you throw away some heat to the cold side like this. So that's the heat engine. You can run the heat engine in reverse, and that's actually not totally crazy to do because remember work done. You can think about the gas, right? How can a container of gas give us some work? It can expand. Right? So the expansion of the gas can be connected to some kind of device that convert this to the work that we want to use it for. So to run in reverse essentially means that instead of having the gas expand, you can compress the gas. So you do work onto the gas. Or in other words, the gas is doing negative work. Okay, but anyway, in terms of the diagram, to reverse the heat engine, you just put in the work instead of getting the work out. Okay, you put in the work, and for this to reverse, you have to reverse everything. So you're gonna have heat flowing into the hot side. You're gonna have heat flowing away from the cold side, like this. Okay, and this is not in violation of the second law because the work done here is coming from outside the system. If you talk about the system to be just the hot and cold side. Okay? And there are a lot of details that you can argue and then think about, but you can be quite sure that this is not in violation of the second law. Okay, and running heat engine in reverse is actually a very important process that we use every day, because what we are trying to do in a refrigerator, right? So what happens if you have a refrigerator and then you just unplug it? The thing like ice cream in your fridge will get warmer and warmer and eventually melt, right? So in order to maintain that cold temperature, you need to always take out heat from inside the refrigerator and then dump it outside, right? So in that case, you can think of the cold side here to be inside the fridge, for example. And you want to maintain this cold temperature, so you want to take out heat constantly, right? So that's why QC flowing this way is also very useful, right? And this is again what we call a refrigerator, which is the reverse of the heat engine. Okay, so instead of getting work done by the engine, you have to put in work. So W is no longer what you want. Is QC actually what we want? Okay, QC is what we want. And the work done is actually something that you need to pay. Okay, so if you think about this, it's a little bit in reverse, right? For the heat engine, what you pay is QH, what you get is W. But in this case, what you get is QC, sorry, and what you pay is W, right? And so for heat engine, we define the efficiency to be the work done by the system because that's what we want, divided by what you need to pay. Now for the refrigerator, it's a little bit different, but we can define also the kind of the same concept, which is the number that tells you how good it is. But instead of telling what the efficiency is, we're going to use a different kind of name, which is called the coefficient of performance. Or COP, and that's defined to be what we want, again, divided by what we need to pay, which is W. Okay, so the reason why we don't call this as an efficiency because the number can be greater than 100%. So it's a little bit strange to kind of define it as an efficiency, but in terms of using this as a figure of merit, meaning that the larger this number is, the better the refrigerator is. It's the same thing, right? But it's just not capped at 100%. That's kind of that's the only reason why we don't call this as the efficiency of the refrigerator. Okay, but anyway, the larger this number, then the better fridge that you're gonna have. So you can see that a very, very good refrigerator is you don't need to put in that much work at all to get some Q, right? So Q divided by small number can be larger than 100%, right? So it doesn't really make sense to define this as in terms of the percentage. But anyway, I think it should be clear if we talk about the refrigerator, what it means to talk about the COP, the coefficient of performance. Okay? All right, so we know what the fridge is. We know what the heat engine is. Now, let's go back to this question, which is why cannot we have 100% efficiency in terms of the heat engine? And you can see that in the end, because it's going to violate second law of thermodynamics, right? So believe it or not, everything boils down to just violation of the second law or not violation of the second law. So let's assume that we have 100% efficiency of heat engine. So we call it a perfect engine here, okay? Now this is very important. We're gonna talk about a Carnot engine in a few moments, right? So the name ideal engine doesn't mean it's the perfect engine. Okay, perfect engine means efficiency is 100%. Okay. Even in an ideal world, usually when we say an ideal case, an ideal world, in ideal situation, is the case where we still need to obey the law of physics. But we obey it in a very special way. For example, we obey it without having to, worry about friction or air resistance or anything, okay? So ideal case means physics is still valid. It just means it's the best scenario possible, okay? So ideal engine have to obey physics, but physics tells us that you cannot have 100% efficiency of the engine, which is perfect engine. That's not ideal, okay? That's even better than ideal. That's when you don't care about physics. Okay, so ideal engine is what we're going to talk about in a few moments. That's what we call Carnot engine. That is not 100% efficiency engine. Okay, I just want to make this point clear, because sometimes when you see the problem is say consider an ideal engine and you say, oh, ideal engine has to be 100% efficiency. That's not true. Okay, so that's a very subtle distinction here. Anyway, let's assume that we have a perfect engine here. So 100% means all the heat that you extract from the hot side can be converted to work. And you don't have to throw away any heat into the cold side. This is perfect engine, 100% efficiency. Okay, assume that we have that. And assume that we have probably not a perfect refrigerator, like an okay refrigerator. An okay refrigerator means that you need to put in some work in order to extract some heat from the cold side. And then you dump everything into the hot side. Okay, so just one quick remark here is that it should be clear from the diagram that work here plus QC equal to QH. Okay, just from the conservation of energy. So what happens is that if you have perfect engine and you have maybe not so perfect refrigerator, you can combine them, because all the work that you get from the perfect engine can be fed into a refrigerator, right? So a heat engine combined with a refrigerator, in the end, what you get is the net effect of this one, right? So let's say this whole thing is in isolated system, right? All the work done is within the system, and that work is being fed into the engine, which is the refrigerator, which is also in the system, right? So if you allow this to happen, right, you're gonna have in the end the effect of heat flow from cold to the hot side. And why is this no sign? Because we just calculated earlier that this violates the second law of thermodynamics. Okay, so the argument goes like this: if we have perfect engine, then we're gonna violate second law of thermodynamics. So that's why we don't have 100% efficiency engine. We don't have a perfect engine, because second law of thermodynamics must be obeyed. Period. Okay, that's fine. If you cannot have 100% efficiency engine, what about, well, 99%? Is that possible? What about 98, 97? So what can be the best case scenario? Like, what's the best we can do in terms of the engine efficiency? Well, the best we can do is what we call a Carnot engine. Which is this one. Okay, so a Carnot engine, again, Carnot is the name of a French physicist in probably 300 years ago. And thermodynamics is a very, very old subject. So people have been interested in the efficiency of the engine many, many years before people think about other things like electromagnetic theory. Okay, because people are interested in how to build a very efficient, steam power train. So this is not, it should be not a surprise to you that people are interested in this for many years already. Okay, for a Carnot engine is the best we can do in terms of the engine efficiency. And just to kind of say what's the most important thing about Carnot engine, and then we're gonna explain this diagram. So a Carnot engine operates between two temperature, the hot temperature and the cold temperature. So I'm gonna throw to you the formula that you need to know. and then we're gonna explain a little bit what it means. So the efficiency, again, is work that you get divided by what you need to pay, which is the heat that you extract from the hot temperature. And this is gonna be QH minus QC divided by QH, right? So this expression is true for any engine that we talk about. Okay, but Carnot engine has one more step that we can say. And again, I don't have time to do a proof of this, and this can be found in the textbook. So I'm gonna write down the result. So for Carnot engine, and this is only true for Carnot engine. For Carnot engine, we can show that the ratio between the heat that you get from the hot side to the heat that you throw away to the cold side is the same as the temperature of the hot side divided by the temperature of the cold side. Okay, so again, this formula here, this is only true for Carnot engine. Okay, any other engine which is not Carnot, this is not true. Okay, you have to be careful in using this formula. But here, the efficiency, that's true for any engine because that's just the definition of efficiency. But for Carnot engine, you have one more step that you can write down. So for Carnot engine, this is true. That means you can substitute this in and then write the efficiency specifically for Carnot engine to be, well, just a direct substitution. So I'm gonna do one step here. So this can be written in terms of 1 minus absolute value of QC divided by absolute value of QH. So we can substitute this ratio into this equation. So this one is not yet Carnot, but this one is for Carnot engine, so it's going to be TC over TH. Okay, so the temperature that the Carnot engine is operated between TH and TC tells you the efficiency of the Carnot engine. And this is the max possible efficiency that you're gonna have for heat engine. Nothing in the world can surpass this. If you're gonna do better than Carnot engine, then you must violate the second law of thermodynamics, right? So when we talk about an ideal engine means you don't lose energy into friction, you don't lose energy into like sound or whatever. Okay, this is the efficiency of an ideal engine, which is the Carnot engine, right? So essentially, we can say that Carnot engine is what we call an ideal engine with the maximum possible theoretical efficiency. Okay, you cannot do better than this. So what is it? Well, a Carnot engine is just like any other cyclic process, is operate within a cycle, and the cycle is given by this PV diagram here. Okay, so there are only two processes that happen for Carnot engine, adiabatic and isothermal. So you have two isothermal here from A to B. That's isothermal. And from C back to D, that's also isothermal. Okay? And I can write it here, so maybe in green. So isothermal. Isothermal is the time where you extract heat from the hot side and then you throw away heat to the cold side. That's the only time where you have heat exchange between the system and the heat bath. Because to join the two sections together, you're gonna join them with this yellow thing. and this is adiabatic. Okay, adiabatic means you don't have any heat exchange between outside the gas container and inside the gas container. So B to C and then D back to A. The only thing happened is whether you compress the gas or you expand the gas. That's it. There's no heat flowing in or out. Okay, so it turns out that if you construct your engine this way, then you get the maximum efficiency of the engine possible, right? You cannot do better than this. And believe me, a lot of smart people have tried to come up with anything better, and you just cannot, because of the second law of thermodynamics. It's kind of capping the efficiency of the engine. Okay, so in terms of the actual operation, like how does it work? So this can be like, a piston in your car engine. And if you know a little bit about internal combustion engine, the work that you can extract to drive the wheels is from expansion of the piston in your engine, okay? And then some of you might have, like some what we call like muscle car or something like that, and you have a really high horsepower. And usually high horsepower means you have many piston that can drive the wheels at the same time, so you have a lot of power, okay? So that should give you an idea like how the expansion or contraction of this can be extracted to be used as work, right? So how does the Carnot engine work? Well, the first step, let's start from A, right? So you have some gas, and then you let it expand, and then you expand by absorbing heat from the hot side, which is some kind of heat reservoir, right? So it's a little bit hard to pinpoint exactly what are we talking about for the heat reservoir. You can think of this as some kind of outside temperature, something like that. So you expand the gas, you let the heat flow in while maintaining the temperature to be always at high temperature, right? So this is what you do. So during this time, that's when you expand the gas. So you're gonna do some work. Not you, the gas gonna do some work. Okay, and then you are done extracting heat. You're gonna be maybe some volume here, and then what you do is you're gonna expand further, but now you don't extract any heat, right? So you're just gonna take the gas container and then you expand it. So obviously, the gas temperature will go down because you expand the gas. The gas is doing some work, but you don't allow any heat to flow in, so it has to come from internal energy, right? So the gas expand and then cool down, all right? So you're gonna let it cool down, meaning you're gonna expand it. So the internal temperature of the gas reaches the target temperature, which is the cold side temperature. And then you want to go back, right? You want to compress the gas, but you're gonna do it such that when you compress the gas, heat gonna flow out to the cold system, to the cold heat bath, right? So you compress the gas here and maintain the temperature inside the gas to be always at TC, the cold temperature. And then once you're done, you take out the cold heat bath and then you compress it further, right? So in this time, you don't allow any heat to flow out. So during this compression, the temperature of the gas will go up. And it's gonna go up until you reach the hot temperature, and then you allow the heat reservoir to be in contact again. Okay, so that's kind of like a walkthrough of this diagram in terms of like how it's actually happening in the implementation. Okay, so we are not gonna spend too much time talking about the detail. Again, the only thing that we need to be absolutely sure that we know is the efficiency of the Carnot engine is given by this formula here. Okay, so in order to kind of, do this, let's just look at this example quickly before the end of our session today, right? So we have a Carnot engine. Well, this is a very important keyword, right? So it's not just any engine, it's a Carnot engine. So that means the efficiency is the max possible. And what we have here is some number, the heat, 2000 joules, taken from the hot side, which is at 500 Kelvin. And we also discard some heat at the cold side, which is 350 Kelvin. Okay, so again, Carnot engine is an ideal engine. It's not a perfect engine. So we need to find the work, and we need to find the heat discarded. Okay, so how do we do that? Well, it's a Carnot engine, and we know that from the problem, the cold temperature is 350 Kelvin. The hot temperature is 500 Kelvin. Okay, and it takes 2000 joules from the hot side. So QH is 2000 joules. So what do we need to find? We need to find W, and we need to find the heat discarded or thrown away at QC, the cold side. Right. So normally, if we don't say that this is a Carnot engine, we really cannot say much. We cannot do anything because there's not enough information. But a Carnot engine, that word makes all the difference. So a Carnot engine means that our efficiency can be calculated just from the temperature. Okay. So again, E Carnot is 1 minus T cold over TH, T cold over T hot, right? So I'm just going back here and use this formula here. Okay. So before we do any further calculation, you can see that efficiency you want as large as possible, right? So that means a better Carnot engine is the one with higher temperature and lower temperature, right? So that means if you operate the engine between two heat baths with large difference in the temperature, that's gonna give you higher efficiency, okay? If you operate the heat engine between the same temperature, meaning that TH equal to TC, then this will be 1, and 1 minus 1 is 0. So you cannot do anything, okay? So in order for heat engine to work, you must have some difference in the temperature. But anyway, we can calculate the efficiency for our Carnot engine. So 1 minus 350 divided by 500. So that's going to be 30% or 0.3. Okay? That's going to be the efficiency of our Carnot engine. And no matter what you do, you cannot beat this. All right, so once we have this, now the next thing is pretty straightforward, because remember what is the efficiency by definition? The efficiency by definition for any engine, that's what we get, which is W, divided by what we pay, which is QH, right? And that's what we try to find, right? Because we want W, and QH is given to be 2000. And then we also know that the efficiency of this engine is 30%, which is 0.3. So solving this gives you the work done given by 600 joules. Okay, so if we were to draw some kind of engine diagram TH at 500K and then TC at 350K, and then we have the engine in between, right? So what you do is you extract 2000 joules here, and you get 600 joules out, right? So it should be quite clear to you, hopefully, that the amount of heat that you need to throw into the cold side is just the difference between 2000 and 600. So that's going to be 1400 joules. Okay, so then we can answer this question. W is 600 joules. and QC is just 1,400 joules. Okay, so that's kind of a really simple application of this Carnot engine kind of formula here. All right, so again, my suggestions is that when you see the term Carnot engine in the problem, just highlight it and then you know you can use this formula here. Okay, so before we finish, let me mention just one small thing. This is Carnot engine, which is a heat engine. So you can also reverse this engine and then get a refrigerator, right? So you're gonna get something which is called a Carnot refrigerator, which is the best refrigerator theoretically possible, because again, otherwise you're gonna violate the second law of thermodynamics. And in that case, this gonna still be true. Okay, so if you have a Carnot refrigerator, remember that you can, so let me write it up here. So you can have the coefficient of performance for Carnot refrigerator. And what is that? Well, let's go back and then take a look. COP is QC divided by W. Okay, and in this case, what is W? Well, it's the refrigerator, so W is again QH minus QC. Okay, so then you can use this to substitute into that, because this is a Carnot, fridge. So you're gonna get TC divided by TH minus TC. Okay, so if you have a Carnot refrigerator, you want to calculate what is the maximum coefficient of performance for this fridge, then you can use this formula here. Okay, so if you were to remember one formula for Carnot engine or Carnot refrigerator, I suggest that you take a look at this one. Okay, because from this one, then you can calculate anything that you want, as long as it operates as a Carnot engine or a Carnot refrigerator. All right, so this actually the end of our first big section of the course, which is kind of like the first half of this course. So next time, which is next Monday, we're gonna start talking about the next topic, which is oscillation and wave. Okay, so I think that's all I want to talk about today. And I have a few minutes, so if you have anything to ask, then feel free to ask. Then if not, then you are free to go. Okay, so this one. Okay. All right, so if you don't have any other things, then take care, have a good weekend, and then I'll see you guys on Monday.